Okay, let's get into waves a little bit more. So consider for a moment a source of waves, a point source like we see here, which is this doohickey. So the idea is that if this is the source of our waves, the rays go outwards from this radially. So each of these concentric circles, I've already labeled it a wavefront, I don't know why I'm labeling again, is a wavefront. So that is some similar part of the wave. It could be the crest of the wave, the top of the wave, it could be the trough of the wave, but it's some part that identifies the wave. So this distance between the wavefronts will be lambda, our wavelength. We've drawn here a ray which traces the outward direction of propagation of the wave. So the ray we can see is radially outward. So the waves are going outward radially. This is going to prove to be a useful model for point sources, sources of light, sources of sound, as you discuss waves. It's pretty common. Not much else to say about it, though, actually. So let's scoot along. Let's now take a look at interference. I don't know why there's a 0 there. That's weird. Be gone, 0. No one likes you. There we go. All right. Interference occurs if I have 2 point sources, S1 and S2, my 2 sources. The rays from these sources are traveling along these 2 paths we consider L1 and L2. Realistically, we have sound coming out. Oh, I don't know when I went back to that. If I were an undo button, I would be there. All right. So we have, radial sources of waves coming out like this. But we can draw a ray along which these travel. And so on a ray, it's just following one sinusoidal pattern. All right? Because we're just locked in at one point here. And so the question is, what do these waves look like when they arrive at P? And so what we're going to say is that they will have some phase difference, phi, between them. And the ratio of the phase difference between them, phi, to 2 pi, one full cycle, will look like the difference in these path lengths over the wavelength. So you can stop for a second and think about this. Basically what we're saying is that there will be a difference in phase, so a difference in where we're at on the wave, recall from last time, relative to the full phase, 2 pi, the full phase of a sinusoidal function, and that this difference in phase is going to be proportional to the difference in path length. So, as we look at L1 minus L2, and we divide this by lambda, this is going to be, some multiple of lambda. We can always force it to be that way. And so the interesting cases are going to be when they arrive, so one wave, so wave 1, wave 2. So when they're arriving in phase like this, so phi equals 0 or phi equals 2 pi, they are in phase, we have constructive interference. Also going to have a case if they arrive, entirely out of phase. I don't know why. That should be a plus. If they arise entirely out of phase, phi is going to be, 180 degrees, or pi. And so we have basically a half integer shift in the wavelengths, right? This is shifted back half of a wavelength or forward half of a wavelength, depending on how you look at it. So in this case, we have constructive interference. In this case, we have destructive interference. In both cases, completely constructive, completely destructive. In between that, you have just kind of a range where you can get kind of anything. That's awkward. I don't know why that shifted up like that. Let's just kind of pull this. There we go. Less awkward now. All right. That's basically all you need to know about that. The whole idea is that in looking at this, we need to look at the difference in the path length, and that is going to dictate just what exactly happens at P. Now, further studies, you can imagine as P shifts, this becomes a very geometrical problem and can get a little involved, but it's kind of fun to look at. Now, one of the other things we need to talk about is this idea of intensity. So we said that when you have a wave. What a wave really is doing, it's the propagation of energy or information, but the distinction between those we'll leave for another time. So the energy that enters at this point now is traveling radially outward. And so the rate at which energy enters this point, the power delivered to that point, is also traveling radially outward. And so our claim would be that the power delivered to both of these circles has to be equal. And this is really a statement of conservation of energy. Whatever energy entered the system at my point of origin, of my source, is still traveling as part of this wave front. It can't be created or destroyed, so it's just getting spread out. I really wish I understood why things disappeared. All right. So our claim is that the intensity, which we'll represent by a capital I, not the current, will look like the power divided by the area. So the intensity will be the power divided by the area. Usually, this will be radial, so you'll have circular areas. It doesn't have to be. You could imagine things that, somehow funnel sound or funnel waves in a certain way without cutting off the signal, although I struggle to think of a case where you could do that without actually losing signal. But anyway, with the exception of a case where you're actually just asked to calculate the power delivered to something, you're not going to, Yeah, so basically this power gets spread out over this area. Right. Anyway, last thing to kind of talk about, Doppler effect. So if we have a point source like this, it sends these waves out radially. Now, if the source were moving, then things get a little different. So my point source is now traveling in this direction. So at the first instant, it puts out a wave. Nope, hold on. Let me think this. So initially, it's at 3 positions, let's say. 1, 2, 3. So the last wave it puts out will be centered here, right, at its 3rd position. The second wave it puts out, will be centered here on the second one. The third, I got my order backwards, but give me a second to finish my drawing. Oof, that was not a good circle. That was actually a pretty solid circle. I'm okay with that. That's kind of more ovalish. All right. So here are our 3 waves. This is the first wave that we emitted at this first point. This is the second wave we emitted at the second point. This is the third wave we emitted at this third point. The idea is that these waves have been coming out at the same frequency with the same wavelength, the same kind of wave. So if we had stayed stationary, we would have had the nice concentric circles. But because we're moving, the center of each of these waves is shifted. So on the leading end, we have this wavelength shrinking as compared to on the trailing end, where it is growing larger. And this is fundamentally the idea of the Doppler effect. We know this most pronouncedly in regards to sound. In terms of sound, we know that the pitch of a note is related to its frequency. So the higher the frequency, the higher the pitch. This means the lower the wavelength, the higher the pitch. So we expect something coming towards us to make a higher pitched sound than when it recedes from us. Train sirens are the big example of this that kind of comes up constantly. We can also do this with light. And in fact, a galactic redshift, blue shift, is one of the strong pieces of evidence for the expansion of the universe. Right, this is the basics of kind of the next level of things we want to talk about here. Kind of this representation of a wave, thinking in terms of wave fronts. This idea of interference, which is kind of the main calculatory piece of this for now. This idea of intensity, which is useful in terms of describing how power gets spread out. And this idea of the Doppler effect, which is qualitatively interesting. It's a good example of, complicating a system of a source of a wave. All right, have fun.